Good afternoon, everyone. Welcome. Welcome, everyone. My name is Carl Mitroff. I am the AeroDef Conference Manager. Thank you all for joining us today for SME's Technical Community and AeroDef Manufacturing Satellite Session. We thank you all for taking time out of your day to attend the Next Generation Automation for Aerospace Composites webinar. We'll get going in a few minutes, but first, I'd like to cover a few housekeeping items. Google Chrome is our preferred web browser for a more reliable experience. If you experience technical issues, please relaunch using Google Chrome. You will recognize right away that your microphones are automatically muted. If you have questions or comments regarding webinar functionality, please use the chat feature. If you have technical questions you'd like to submit to our panelists, use the Q&A box. We'll be on both. And in the event of any technical glitches, we are recording this presentation and it will be made available on our AeroDef website. Finally, enjoy today's webinar and the opportunity to hear from today's aerospace leaders. Today's webinar on the next generation automation for aerospace composites will discuss the state changes that must happen in the aerospace industry to achieve production rates for future aircraft. We'll address how the automation of composites is going to be a major component to enable the next generation of aircraft. This panel will explore the possibilities of automation that can provide solutions to the aerospace industrial base. Today's webinar is moderated by John D. Russell. John is the Chief of the Air Force Research Laboratory Structures Technology Branch. He is the Senior Manager of an 18-person team that develops and transitions new airframe structure technologies for safety, reliability, affordability, and efficiency in the current and future Air Force weapons system. One of the nation's leading experts in composite materials. Dr. Russell has a Doctor of Science degree in Chemical Engineering from Washington University in St. Louis. He is a Fellow of SME, and the Air Force Research Laboratory. Dr. Russell has been an SME member since 2017. Thank you, John, for moderating today's webinar.
All right, thank you, Carl, for that introduction. I appreciate it. And thanks to everybody who's joined the webinar today. Just as background, we were supposed to be doing this live at AeroDef back in March, but AeroDef went down just as the coronavirus started to hit and everything started to topple. But we're all excited today to be with you to share our thoughts on what's going on with next generation automation for aerospace composites. So I've got 4 panelists with me today, and what we're going to do is each of us will give you just a few charts as to what some of our research interests are, and then we'll get into a question and answer session. So I'll be starting off today. So next chart, please. So as we look to what's been going on in the aerospace industry, especially pre-COVID, because that's when I started to do the research in this, there are several drivers that all lined up together look to put a lot of stress on the aerospace industry in terms of the production of composite materials. First of all, there's been speculation that over the next 20 years, the airlines are going to have to buy 40,000 new airplanes. And to put that in context, I think right now there are about 20,000 airplanes currently in the fleet, or at least as of pre-COVID. You look towards military, there's been a lot of talk about attritable aircraft systems working in tandem or alone with the manned fleet. These things would have a different way of operations. We wouldn't be flying them 20, 30, or 40,000 hours like conventional military aircraft. These things should be so cheap that if they get shot down or if there's a defect, we can just discard it and replace it with a new one. So with this, we're talking about building these things in the thousands if these kinds of aircraft are going to be on the order of 3 million or less. So very cheap in terms of military cost. We're also looking at potentially multi-variants, maybe on the order of 10, 15, 20 different variants per class, and rapid spiral development so that as the threats evolve, we can adjust the capabilities of each aircraft accordingly. Then finally, there's been all this talk about urban air mobility. You may have heard the Air Force and its Agility Prime effort, which is trying to catalyze the urban air mobility and see what we can do to make use of it in a military application. But the whole air taxi concept is getting a lot of attention, and there's talk about building these things in the tens of thousands or hundreds of thousands. So perhaps the construction on these are going to be more car-like. So all of this is also going to add up to designs with bigger and or more complex composite structures than have been built to date. And factory throughput is going to be a huge issue. People are not going to want to build new factories. They're going to want to take advantage of the space they have and see if they can be more efficient in terms of putting things down the production line. So lots of stress on the industrial base. Right now, we're doing a lot of hand layup. There is automated toe placement and fiber placement, but relatively speaking, they're slow and they're really most efficient for mild curvature only. And current construction techniques still today are more analog than digital. We do asset tracking and we do process measurements, but we're not really in the true Industry 4.0 environment for aerospace composites. So next, please. So back in the fall of 2018, AFRL sponsored a workshop to try to get a handle on where we needed to make future investments to address some of these issues. Two of the key areas here I'm going to address, first of all, is low-cost, agile manufacturing, where in the future state, we look to have a full understanding of our process capabilities, and we have a goal of a 50% reduction in the design and manufacturing cycle time so we can meet those rapid spiral development rates. We also want to be able to rapidly reconfigure manufacturing lines to meet various product mixes and perhaps surge demand if maybe we need to break in and take over somebody else's production line so we can surge when we need to build a lot more of these things. So solutions to that, one area is to look at the cure cycle. If you look at traditional aerospace epoxies, it takes forever and a day to make a part in an industrial size autoclave. How can we be aggressive about the cure cycles to really cut those autoclave times down, maybe even in half? But also we want to look hard at automation. There's a lot going on in automation for automation's sake that the Air Force Research Laboratory is either sponsoring or leveraging from other research efforts like collaborative robots, robots that interact with humans, flexible robotic systems that can be reprogrammed much easier than today. So really reprogramming on the fly as needed. We want to improve the utilization of fiber placement equipment and really ramp that throughput up. But also in areas right now where we don't use automation that are really more appropriate for hand layup, we want to see if there are solutions to do robotic layup and forming of complex shaped parts, both in the thermoset as well as thermoplastic. So next, please. Then the other big area to share with you is quality assurance. So, in the future, we would love to have quality assurance in line with the process and as an alternative to post-process inspection. Post-process inspection is a cost, and it's a rate-limiting step for suppliers to get parts out the door and to get paid for them. And really, these in-process sensors applies both to as manufactured as well as in-service conditions. Could we use sensors in service as well to address the state of the airplane? So some potential solutions. I mentioned we're not really employing Industry 4.0. How can we use those kind of tools to provide an understanding of the state of the part? What can we do with artificial intelligence and machine learning to improve throughput? There was work as neural nets were in their infant stages back in the late 80s and 90s, that really has stood still since then. How can we use that to improve the way we build today? But also a couple things I stole from Anish, who'll be talking later. How can we move from inspecting parts to actually measuring parts? And how do we marry simulation environment with that process measurement so we can have a continual feedback loop? So with that, that's just a few things I wanted to tease up with everybody today. So we're going to move on then. Next up is going to be Dr. Anish Pasartip. So Anish is a busy guy. You can see he has 3 jobs here. He's a professor in the Department of Materials Engineering at the University of British Columbia in Vancouver. He's also director of the Composites Research Network and also director of research with Convergent Manufacturing Technologies. So Anish has worked in digital manufacturing for over 30 years. He's focused on the manufacturing of advanced composite structures, primarily for aerospace. Anish is a recipient of the Medal of Excellence in Composites from the University of Delaware and an ASTM Wayne Stinchcomb Award, and he's a fellow of the Canadian Academy of Engineering, ICCM, and SAMPE. So Anish, over to you.
Thank you very much, John. If we could go to the next slide. John's given a great introduction. So what I'd like to do is just sort of walk us through some thoughts on what would next generation composites automation look like. And the reality is, if you look out there, digitalization is with us. Industry 4.0 is the talk of the town. Automation is considered to be so 3.0. And yet we have to be honest and acknowledge that in composites, we're lagging even in the adoption of automation. So we have to ask ourselves, why is that? Because only then can we actually move forward. The thing to realize is that the value of composites production is really quite high, but our volume is small. To give you an example, if we think of a twin-aisle commercial airplane being worth $100 to $200 million, that's the equivalent of 100,000, 200,000 smartphones. And so you can't just blindly apply lessons from the other sectors to us, because a couple of 100,000 smartphones, that's a lot of repetition, whereas the whole point of what we do is that we have total difference in every piece of the airplane. And so as we look at how do we do it for our own sector, and we look at how do we actually automate, the other point to make is that our industry grew back in the 60s and 70s. And so the current paradigm, the way we do things, all the way from designing to producing to certifying, are built on what was available in an analog era. So we don't want to automate the current paradigm. We actually want to look forward how automation will change the way we do things, all the way from designing to manufacturing to in service. Next slide, please. So if we focus on automation per se, the classic automation paradigm is sense, think, you act. And so the real fundamental questions we should ask are, what is it we should sense? How should we sense it? And then why? What are we going to do with it? If you actually look at some of the trends in composites manufacturing right now, people are actually trying to avoid measuring things. And the reason is we don't know what to do with our measurements right now. So we've got to overcome that. Then we got to ask, do we have enough data? If we don't have enough data, how do we generate the knowledge? The next point is, we shouldn't look at just one cell in the factory. We should look across the whole factory. There's no point optimizing something in one cell if that benefit disappears in the next cell, or vice versa, if something we do early on affects things downstream. If my out time in my AFP cell affects my cure, I need to understand that, I need to manage that. That actually then takes me to, when I do things in the factory, how can I actually have the right level of accuracy, the right level of capability? All of this goes to realizing that what we're trying to do is trade non-recurring cost with hopefully decreased recurring cost. So it's all about a trade-off between cost, rate, quality. And within that, we have to realize that there's a perverse effect of automation, which is that you actually front-end load your risk. Once you buy that automation, you're stuck with it. So you'd better make sure that it works. John alluded to this issue of agility, of being able to be versatile. How can we make sure that when we go to automated systems, we still retain that ability that humans have to change things on the fly? And again, the thing I really want to emphasize is that the biggest investment we make, even though we tend to think about the product, is we're building a factory. And if that factory can be used not just for this product, but for other products, then of course you're amortizing that non-recurring cost effectively. To do that, you really need to think about the transition from the world of today to the world of tomorrow, all the way from existing factories, how do we automate existing factories, through to how could we go to a world of the future, that Industry 4.0, which beckons in a way that is actually tractable in all the ways that we need to do it. Next slide. Thank you. So it is my firm belief, and I would argue this quite strongly, that the only way we're going to succeed in doing this in the composites arena is by fusing classic Industry 4.0 with a product materials-centric integrated computational materials engineering approach. In other words, your digital thread has to be science-based. It's the only way we're going to allow for all the complexities that exist in composites manufacturing. That would allow us to link materials design to product design, to factory equipment design. It allows us to do the things that John alluded to in terms of turning inspection into a value-added activity. And it would actually allow us to then create certification and regulation in the way that works. In terms of my own work, at UBC, we're really pushing what we have developed over a couple of decades in science-based simulation into production. And we're reimagining how research and education occurs in such a world. We're talking about how if medicine is teaching hospitals, why don't we have learning factories in engineering? And obviously there would be digital learning factories. And we're bringing a much bigger group of stakeholders to play. And at Convergent, our focus is very much pushing simulation-based capabilities into the factory, fusing science-based simulation and data science. Because without that, we genuinely don't believe that we can really disrupt the world with automation. With that, I'll stop and hand off back to John.
All right, thank you, Anish. So next up is Waruna Seneviratne from Wichita State. Waruna is director of the Advanced Technologies Lab for Aerospace Systems, or ATLAS, and he's senior research scientist for composites and structures at Wichita State's National Institute for Aviation Research, or NIAR. So Waruna is responsible for a research portfolio that includes projects from the FAA, DoD, Homeland Security, NASA, and aircraft industry in the areas of advanced manufacturing and inspections, durability and damage tolerance, certification, and structures. So Waruna, over to you.
Thank you, John. Thanks for the opportunity, and glad to be here with this very reputable panel. This Industry 4.0, this demand for high-rate aircraft manufacturing, flexible rates in this digital engineering, it's real. It's coming, and it's already here. So as educators or research institute associated with the universities, what are we doing? So hopefully through my presentation, I can give you a quick overview of what our plans are. So this last year at Wichita State, a National Institute for Aviation Research, or NIAR, we have about $30 million investment, not just the university, but the DoD, the Army, Navy, Air Force, as well as industry. You're talking about equipment manufacturers, software vendors, and all of these invested on ATLAS, which is the Advanced Technologies Lab for Aerospace Systems, to address this demand, primarily to address this demand. So the mission of ATLAS is to develop a multidisciplinary manufacturing environment, not just focus on AFP, not just focus on manufacturing, just like Anush alluded to, the digital engineering that includes the design, the manufacturing simulations, process simulation, all the way to the certification and even sustainment. So create a multidisciplinary manufacturing environment and an engineering education program to prepare not only our engineers, also the educators for the factory of the future. In addition, sorry, my mission statement got cut off a little bit there, but in addition to aid the current workforce seamlessly adapting to this manufacturing digital engineering that's coming in the future. So the approach we have is a three-pronged approach. I call it a past, present, and future. So we've done a survey with our local industry here a few years back about how long it takes a fresh engineer to become productive in an industrial environment. It actually takes about 2 years for a fresh graduate to become productive in an industrial environment. And even with co-op type of education experiences, that 24 months probably cut down to about 18 months. So that's a huge investment for this industry, and this is traditional manufacturing type of activity. So when you talk about this advanced manufacturing with artificial intelligence, machine learning algorithms, and so on and so forth, there's a huge demand for this in the future for these type of engineers. So part of Atlas, and then the thing is, because of this time requirement, most of the companies tend to outsource their the engineering. So a part of Atlas' mission is to create a pipeline of industry-ready future engineers, so that when they leave the university and join the industry, they are ready to work literally the next day. And the equipment that we are integrating into Atlas, they are same all the way from lab, tabletop, all the way to the industry scale manufacturing. So it's a one-to-one scale. So whatever the research they are working on, it's directly applicable all the way from process development all the way to a manufacturing environment. And in the present is where we work with the industry continuously and solve their problems. If you look at most of the industry, the research labs that has this type of advanced equipment, they're always busy solving current manufacturing problems. Hardly have any time to do research. So Atlas this type of research institutes become an extension to the research facilities that industry has. Like Anush alluded to, you make a big investment, you need to make sure this multi-million-dollar equipment is actually going to give you what you're looking for. So Atlas not only become a extension to the industry R&D labs, they get to come to this type of environment and actually test out their manufacturing. The prototyping and things like that, because we have multiple machines, multiple software, multiple ways of manufacturing. So the industry can actually, before they make that investment, they can evaluate, is this the right investment? Is this the right way to do this? And then the past is basically, every time you talk about automation, some people say, oh, you're going to take our jobs away. It's quite the opposite, right? If you were to plan everything in a strategic way. In other words, you're making 10 fuselages a month now, and you make, with automation, you may increase that to 15. Now that's 5 extra fuselages that you have to put wiring, controls, and this and that. So the automation actually has the capability to increase our job. And the past essentially focus on this current workforce that are engaging in the traditional manufacturing, that are worried about losing their jobs, basically create workforce training programs that train this current workforce, not only the future workforce, current workforce. So we'll be developing a lot of training programs. Next slide, please. So in Atlas, one of our largest programs is from the AFRL. It's called Modeling for Affordable Sustainable Composites. We are focusing on several manufacturing segments like automated fiber placement, compression, injection, and overmolding, use of thermoplastic welding, and so on and so forth. But this, I don't want to go into too much detail, but this is a great example of how manufacturing can significantly influence our rates, right? So you can see here, we go through the design, we go through our manufacturing simulation. So we're already using digital engineering in our manufacturing. We basically go through our manufacturing simulation, the one you see on the top in the middle. We basically simulate the entire manufacturing process to make sure that our robot's not going to hit one of the tools and so on and so forth. But what we're trying to do here is, if you think about actually making the AFP or the automated fiber placement part, we make a layer, we stop the machine so we can go and do our manual inspection. So every layer you're doing this manual inspection. So think about, you're wasting 30 to 70% of your manufacturing time just posing this multi-million-dollar equipment and doing manual inspection. So think about putting a in-process inspection system on your robot, so that robot, while you're manufacturing, you can actually do your inspection. It sounds easy, but you need to make sure whatever the tools that you're using here is not going to give you false alarm or has the ability to detect the defect or don't miss anything in an important area, has a higher probability of detection. And once you generate all of this massive amount of digital data, what else can you do with it? You can actually use this digital data through artificial intelligence algorithm to detect patterns, pattern recognition. Today, we do this manually. Our NDI groups go through every part that comes out of and then they look at all the NDI history and see, do we have any defects in same areas, maybe because of our tooling and so on and so forth. We're basically creating this manufacturing, these algorithms and artificial intelligence algorithms for detect these anomalies and also use to improve our future manufacturing process, so that we can increase the rate, improve the quality, and reduce the overall cost. Next slide, please. So in order to do so, in order to tackle this, we obviously will build several partnerships, and this is one example. And you start, we're working with the future generation as well as the industry. So we start from the tabletop flat panel inspection using handheld instrumentation to make sure our algorithms have a higher probability of detection as well as low false alarm and so forth. And then we need to integrate this into a robot, make sure it still works, and then slowly climb up in the building block to a industrial scale robotic manufacturing system that is actually manufacturing a double contour and aircraft structural part. So with the what I call an Atlas or the maker space that we have built, it gives the students and the industry to take a concept at a low technology readiness level from a concept stage to a tabletop experiment all the way to the manufacturing scale. So your scalability of your research is a one-to-one. That allows the industry to come to the university, just bring their tools, just bring the exact same program that they would use in their factory floor and do the manufacturing research, make sure everything works, and take that to their industry flow and basically carry on to the next step. And small to medium-sized businesses that doesn't have access to these type of equipment, it basically become a maker space. It's a level playing field that anybody can come and have access to these type of equipment. Thank you.
All right. Thank you, Roberto.
Sure.
So let's move on. Robert Harper. So Robert's the Director of Technical Sales and Market Development at Thieves Machining Systems. At Thieves, he works directly with the technical teams of large aerospace companies and component suppliers to those companies, offering technical guidance leading up to delivery of tailored manufacturing solutions to maximize total part throughput. So, Robert, over to you.
Thanks, John. So this is from a machine tools perspective, machine tool manufacturer's perspective, though. So my headline here is how do we go from 14 to 60? And so if you look at today, the first two programs with heavy composite content and I would say heavy automation was both the 787 and the A350. The 787 peaked at 14 ship sets a month, 168 a year, and then the A350 peaked at 9.5. In the future, when that's going to happen to address John's initial statement of going from 20,000 to 40,000 aircraft, a future single aisle for either Airbus or Boeing at some point are going to need 60 plus per program per month, which is significantly higher than what we've seen in the 87 and the A350. So if you just use the 787 today just for the fuselage, not including any stringers, just the skins of the fuselage, I believe there's 19 fiber replacement machines that are used to produce those parts. There are 19 pieces of equipment around the world to produce 14 ship sets a month. Now, if you take that and you say, okay, for a future aircraft of 60 per month, you would be upwards of, for just one program, 100 or 50 machines at the same rates that we lay up today. If you multiply that by 2 programs, you're at 100 machines worldwide if we stay at the same rates, same overall laydown rates that we have today. Change slides. So what do we need to do? So in order to be able to produce equipment for these future aircraft programs, and again, I'm just talking about one program. There's multiple programs, military programs, there's space programs, there's going to be UAV programs, but just focusing on just the single aisle, which will be the highest production. There's several things that need to happen. First is we have to lay down material fast, but that's only a piece of it. Higher reliability, which is probably the largest piece, is really to keep the piece of equipment running. And when I say higher reliability, that means not only the reliability of feeding material, but it's feeding material, putting it on the tool in the right spot that doesn't need rework. That's reliability to me. So we need to have a lights out mentality of building equipment that runs reliable with very little intervention. Next is we need to automate the secondary processes, and this is probably one of the biggest things. Most customers today, everyone worries about pounds per hour, and make the machine lay faster. The machine is a small piece. Rowana just mentioned it in his intro, is that inspection and other things make up the majority of the time. The cycle time is in a lot of cases a small percentage of the overall floor to floor. The secondary processes like tool load, unload, machine alignment, material replenishment, offline maintenance, and process inspection, those are key areas that need focus to add automation to make these parallel processes instead of serial processes like they are today. Next is simplified operations. We need to make the machines simpler. We need to make the machines so that you don't have 4 or 5 drill down screens to get to. We need so that operators, it's very simple for an operator to run the machines. We don't, in most cases, you don't have engineers running the machines, and although they are multi-million-dollar pieces of equipment, we have to simplify the operation, which then would eliminate some error on the operator's part, ultimately adding to that overall time. Lower cost of ownership, so the pieces of equipment, to own the piece of equipment, not just the purchase, the capital cost of the equipment, but it's the cost to own it over its lifetime, is so that the replenishment of consumable products, cutters, compaction rollers, and whatnot, that they're significantly less cost than what we have today. Something else is alternative material types and formats for particular part types. So it's not just going to be unidirectional thermosets. We need machines that can do out of autoclave, thermoplastics, dry fiber, uncrimped fiber, CMCs, and in also varying thicknesses and width that are tailored to particular parts. Today, sometimes we try to take an off-the-shelf or catalog machine and make it do everything. So you're going to see, I think, more tailored to particular types of parts. And overall, this entire list, and I'm sure quite a bit more, we need to see 2 to 3 times faster floor-to-floor throughput over the current technologies. And so that's from the time I put a tool into a part or into the machine, and I pull the tool back out with a part on it, which is what I consider floor-to-floor. So, thanks, John.
All right, thanks, Robert. And now our final panelist is Bob Kuhn. Bob's a Lockheed Martin Fellow in Materials and Processes with a specialty in composite materials and automated processes. So over the years, he specialized in the automated fiber placement, innovative low-cost composite manufacturing techniques, computational methods, material characterization, and polymer coatings. So Bob, over to you.
Thanks, John. So this session's topic actually is real near to my heart, since, as John mentioned, my fellow appointments associated with automated processes. My intro comments are going to touch quickly on a couple automation-related topics that myself and my skunkwork colleagues are working on. So for this first topic, we'll start with automation and the Air Force efforts associated with and directed at the low-cost attritable aircraft that John summarized in some of his intro comments. Lockheed Martin's approach to cost and cycle time improvements on the low-cost attritables are heavily tied to automated processes, examples of which can be have been applied on our ongoing Wisdom program that we have with John's group, in which we're using fiber placement, long fiber injection, continuous fiber 3D processes to build each of the wing box components. We're looking to leverage lower cost and more rapid cycle time methods from other industries, in particular the automotive industry. And by doing so, we're sacrificing some of the performance that we might gain when we gain the cost and cycle time improvements. But we really don't need 5-minute cycle times that are common in the automotive industry. So we can substitute higher performance materials, specifically the resins, to find a compromise between performance and those cycle time improvements. Another comment on hard tooling costs and the lead times associated with high rate processes like compression molding, however, really aren't compatible with the low cost attritable requirements due to the anticipated production volumes for the LCAAs. Hence, we really need innovations in tooling or use processes that don't require any tooling at all, which are basically additive type manufacturing approaches. Until bonded assembly automation is more mature, we're targeting within Lockheed the auto drill and auto fastening applications of assembly. So our focus on automated processes also supports the Air Force low-cost attritable goals for reducing volume and rate cost dependence by basically minimizing the training needed for skilled labor and permitting pre-production learning via model simulation. Next slide, please. So in contrast to the smaller unmanned systems, we also have ongoing efforts directed at applying manufacturing lessons on active programs to plan for automated manufacturing of next generation transports and tankers. One objective of those efforts is to eliminate or drastically reduce the need for assembly jigs using simple access stands instead of leveraging self-locating design features like determinate assembly that we've developed on the F-35 program. And what we call radical affordable manufacturing efforts we're pursuing flexible large aircraft mating concepts, and those include automated optical alignment systems that allow for automated mate and demating of really large assemblies for drilling the combined assemblies like the forward and the center fuselage sections of these large aircraft, and then demating them for destack and deburr, and then quickly relocating them together again. The concepts also include common actuator packages for the XYZ translation of these large subassemblies. Those development efforts are also evaluating extremely low-cost tooling and assembly development targets, targeting large additive tooling systems like the BAM, as well as additive manufacturing of metallic locating details for pi preform bonded assemblies. The digital tapestry or digital twin topic is all about providing a digital representation of the as-designed condition and then using that information to provide virtual reality on the shop floor, which includes, say, projection of the work information directly on the aircraft. An example of that is where we are projecting systems for mold-in-place coatings, low observable coatings on the F-35 program, and we expect to apply similar technology on the KCZ tanker program. That digital twin will be linked to the shop floor for immediate application using robotic applications and allowing for rapid changes implemented there on the shop floor. An example of the flexible automation assembly is our automated fastening system, which optically uses a robot to recognize the part and location on the aircraft and then the local features, and then uses a laser scanning system to generate a point cloud, and then provides for the robot path plan for installing the fasteners. The system also uses AI to adapt the path as more articles are then fastened in the future. Hence, this system provides kind of a self-programming and adaptive path programming method. The last slide, please. Within the skunkworks organization, the topic of automated manufacturing is a hot topic. That's because our newest production facility, which is currently under construction in Palmdale, California, covers about 200,000 square feet, and it's slated for starting up in May of this next year. This investment's showing our near-term commitment in capital, anyways, for automated manufacturing. There's an interesting challenge that's posed with this facility to our facilities and our management teams that's regarding how do we provide a highly automated environment that's also a classified environment. And, while I can't touch on much about how we're tackling this issue, suffice it to say that all that interconnectivity is going to largely be restricted to the building itself. So it's going to be one giant Faraday cage, and all that automation stays within the building itself. As you might expect, facilities design is tailored to a flexible factory floor, where the in-ground connectivity to the robots is in combination with a high reliance on flexible robotic systems, some of which was talked about a little bit earlier, and allowing for a rapid reconfiguration of the manufacturing layout as designs and the vehicle variants change. John, that's it for the slides.
Okay, thanks, Bob. So with that, we've got a few minutes to have questions. So I've got a few to tee up, but I encourage anybody who's online to put questions in the chat so we can pose them to the panelists here. So first of all, I want to ask about so what are some technologies in other industries that we in aerospace need to pull in to look at to improve automation and to improve throughput in general? So let me start with Anush first, because I know you've been thinking about this space. Oh, you're muted, Anush.
Sorry about that.
You buy the first year.
So what I would quickly say is that if we look at all our other sectors, they're much more digital than we are. If you look at automotive, they do all their design digitally. Everything is transmitted into the factories digital. They measure a lot more than we do. And so I think the biggest lessons we can learn from other sectors is how have they created value from those digital technologies in the whole life cycle. I think we're at the moment taking very small incremental steps. There's good reasons why we're doing that. But I would argue it's about a holistic approach to going digital.
Okay. Bob, let me ask you the same question. I know you're involved with Acme, and they are looking at more automotive. What can we gain from industries like automotive and marine?
Well, I'll tell you, it's one of my self-imposed job descriptions to survey the other industries, non-aerospace industries, to look how to implement some of those technologies into some of the activities that we're doing, including programs like your Wisdom program. As I mentioned in my introductory comments, the low-cost attritable goals for more rapid cycle times and lesser cost dependence on production and volume are ideally suited to adapting lower cost composite materials and automated manufacturing methods. And within that Wisdom program, an example of how we've done that is to use that long fiber injection process. For anybody not familiar with that, that technology was developed for the manufacturing of John Deere tractor hoods, and it's used manufactured over at Romeo Rim in Romeo, Michigan. Their process is well suited to rapidly processing composites that have the potential for particularly high fiber volumes at fairly low pressures. So it can be if it can be adapted to higher performance fibers and higher performance resins, I think that kind of technology will have huge opportunities for these future basically kind of plagiarizing some of these technologies that are coming from non-aerospace industries.
Okay, thanks. All right, we'll switch questions here. I've got one more before we dive into what the audience has to say. So, Varuna, what's the role of a university in developing new automation solutions for aerospace composites?
So as a university, you don't really make aircraft, but one of the luxuries we have working with the industry is solving problems. Our students day in, day out, like a fire team, right? So that actually opened their eyes to the challenges that industry faces. So one of the technologies that we work with is a microwire system that can control that can basically instead of using our manufacturer recommended cure cycles, how can we use the material state of a part in order to do a cure? So in other words, instead of using time temperature type of traditional ways of cooking and composite part, can we use the viscosity changes, for example, to control the autoclave? So basically, we use the Anush's the Compro software, and then combine that with a microwire sensor that can actually monitor the viscosity of the material, and use that information to control the autoclave. Now, we can come up with these type of concepts, but as an industry, you need to take it to the next level. Okay, the reliability. How can we certify this process and things, and these type of things. So when it comes to structural certification, I think in IR we have a lot of experience as far as certifying this revolutionary or new manufacturing process. This is where we need to bring industry and kind of do lots of trials and errors to make sure that it actually fits well with what the industry wants to do.
Okay. Then Robert, to spin that question a little, you as a component or as a tool manufacturer, how do you guys look to use university to help you improve your products?
Yeah, so it's a great question. So one example is we are using the Canadian National Research Center out of Maribel, Canada. We teamed with them to develop an inspection platform, an in-process inspection platform. We had worked on our own on several different technologies, line laser and triangulation. And Ali Yusufer and his team at the CNRC came to us with a technology which also addresses your last question of using technologies outside of the aerospace industry, where we teamed with them on this optical coherence tomography technology to use that technology for in-process inspection. on the machine. So we are currently partnered with them, and we have other projects that we are looking to partner with both universities and these state-run labs.
John,
Okay, thanks.
if I could add a word to what Varuna and Robert just said, I think one of the things that's going to change dramatically in the role of universities is, classically, we've always done education and research. Our research has always been low TRL levels. Talking about learning from other sectors, if you look at medicine, in medicine, a teaching hospital is where education, research, and practice come together for maximum value. So one of the things that digitalization will hopefully allow us to do is allow universities to do what they're good at, which is education and fundamental research, but in a way where that knowledge can be transitioned through to industrial applications. So I think a really good question to Bob, for example, would be, here they have this brilliant factory of the future coming online. Clearly, it's in a Faraday cage, as he said, but how does one take that data, anonymize it much like medical data is anonymized, and then allow lots of academics to work on it in terms of the fundamentals and then feed it back into the system? How do we actually collapse the concept of TRL levels that we have at the moment?
I didn't know panelists were allowed to ask other panelists questions, Anish. That's a bit, and I really don't have a good answer to your question anyways. I believe that that's the sort of thing that some of the manufacturing engineering and in combination with the facilities folks that are setting up that system are trying to understand how best to use that automated data, because this is a new paradigm. I mean, the amount of data that they're going to have available to them as a result of everything basically being censored is going to allow huge opportunities they're not even aware of right now, and they'll learn as they go, basically.
Okay.
I was trying to put you on the spot.
Let's switch topics a minute. There's like 3 materials-related questions here from the audience. Let me kind of roll them all up into one. So, do we expect any material changes in terms of form or function in order to increase throughput or to meet specific design needs? And what consideration may we have in aerospace for things like natural fiber reinforced composites? So that's a lot to chew on, but let me just throw it out to the panel as a whole. Anybody want to take a first crack at that? How about Bob?
This is Bob. I touched on this issue a little bit earlier. For instance, what we're doing a lot within our activities to support the low-cost attritables is we're plagiarizing technologies from the automotive industry, but in many cases, those processes do not give us the performance that we need for the low-cost attritables. And for us to be able to get those performance levels, we're going to have to change materials. And a lot of these processes, like the long fiber injection process, as an example, are very much suited to trading out. It does require changes to the hardware. If you change out the resin system and it's more corrosive resin, for instance, you have to change the resin handling systems and the seals used in the process to spray the material. So it's not a simple exchange from material A to a higher performance material B, but with a little bit of development effort, I think the answers to some of those questions can be addressed.
One thing I've noticed is that as we look to try to do cheaper systems, the powers that be still want the same kind of performance, particularly on the military side, but I don't see any dialing back of performance in commercial either. So I think things like natural fiber composites are going to be relegated to interiors. But if you're talking about primary load-carrying structures, we're going to be looking at the tried and true materials, maybe a little spin on it for more improved processability or laydown or things like that. Anybody else have a comment?
Yeah, so John, I'd like to add, obviously as a machine tool manufacturer, we want the material to be as thick and wide as possible to increase the pounds per hour, but most of the programs today are going the exact opposite direction. They want thinner material so that they can place as thin layers as they can for the best engineered product, which goes the opposite direction as far as pounds per hour. So that's part of what I was saying earlier is, reliability, using these thinner materials, which are less, weight per square meter, We need to be running, machines have to be pretty much lights out, in high reliability, putting the material down where it's supposed to be, the way it's supposed to be the first time.
Okay, thanks. All right, another question here. So in automotive, we see a high degree of automation, but the thing that lends itself to automation is it's a very low number of products per production line. Where some of the things we're talking about in aerospace is maybe having automation help us rapidly transition to the manufacture of rapid products, or do we think that that's a doable that we can do a high mix of activities through automation, or is that going to make manufacturing multiple systems more difficult?
Well, as Bob, I can touch again on a topic that's related to that I addressed. I think the big hurdle for us to transition those kinds of technologies that are automotive over to aerospace is going to be tooling. The number of ship sets that we're going to be manufacturing, even if they're low cost, attritable unmanned vehicles, are going to be hugely smaller numbers than the automotive industry deals with every year. And the only way we can be competitive in those kinds of processes is to find tooling options that get us away from the match mold steel tool approach that the automotive industry uses so extensively on things like compression molding and so on. And there's opportunities there. There's a number of these material systems that are already proving out in some evaluations that we've done in-house that they don't need 1,500 psi of pressure to compression mold a lot of these materials. You can get exceedingly good properties, certainly good enough for a lot of the low-cost attritable market at pressures that might allow us to get away with additive tooling.
Okay.
John, if I may jump in, and if you think about the automotive, they're talking about making a part in a few seconds. Right? But aircraft, the aerospace industry doesn't have that type of rate requirement, at least yet. But the quality, right? So the quality has to be significantly improved. The repeatability has to be there. So there are certain lessons we can learn from automotive industry, but there's a lot to be done in order for that technologies to meet the aerospace requirements.
Okay.
And if I could add one observation, if you look at production run sizes, even putting aside supercars, which are worth millions, the smallest production runs in automotive are tens of thousands, hundreds of thousands. So your whole mentality to deal with your non-recurring costs are dramatically different than anything we do in aerospace. And if we want to learn from automotive, we have to pay attention to those critical differences.
Okay. Well, with that, it's 3:59, so this is supposed to be an hour. So I just want to wrap things up. First of all, I want to thank all the panelists. So Robert, Bob, Waruna, and Anush. I'm glad you can make it here and share what each of you are doing in terms of next generation automation. Really appreciate your input here. And again, sorry we couldn't do this in person. I miss seeing you guys, and eventually we'll get there. Just as an advertisement for the audience, so AeroDef is going to happen next September. So look for announcements from SME on that. Hopefully by then we're through there. We can all get together in person. We'll be really excited to get together. So I want to thank everybody. We really appreciate your time and hope you have a good day. And Carl, any last words from SME?
Yes, thank you, John, and thank you everyone for participating. Great discussion, super informative, and really appreciate the time and investment that you have all made for us. So thank you very much for supporting, for putting time to support us and SME events and the entire manufacturing community. Be on the lookout. The only thing I really have to say is special thanks to all the attendees who participated. Note that we are going to distribute a quick post-event webinar survey, and we would appreciate your time in providing feedback to help us continuously improve. And be on the lookout for the next webinar, Continuous Innovation and Development of the F-35 Program. That's going to be hosted by Don Kennard, PhD, Senior Fellow at Lockheed Martin Aeronautics. That's scheduled for November 15th from 3 to 4 p.m. Eastern Time. Registration for that webinar is now open. And again, just want to make sure one more mention that this webinar has been recorded and it will be made available on the Aerodef event website. There you also find previously recorded webinars on that same site. So thank all the panelists and the moderator and John, thank you very much. And all of our attendees, thank you for your time. And we hope to see you next time on the satellite webinar series. Thank you very much.
Thank you.